In this video, we would like to introduce and discuss the LP spaces. In a previous video, we have already examined the L1 space, for which the main properties are pretty straightforward to check. The only thing that is a bit harder is to check that the infinite dimensional L1 space is complete. And now, for the LP spaces, proving the triangle inequality is much harder, but we have already established in the previous video the Minkowski inequality, which is pretty much all we need. And again, the difficulty will be just to show that it's complete, but this is done pretty much in exactly the same way as we did for the L1 space. So we will just give the outline and leave some of the details, but let's get started. So let's start with the finite dimensional analog. So let's say that n is in n, a natural number, and that we have fixed. And we equip Rn with the norm so to the vector x1, xn, we attach the so-called p-norm, which is precisely the sum from k equals 1 to n of xk's to the p all raised to the 1 over p. And of course, we need to ask ourselves why this is a norm. So let's check the properties. So the first thing that we need to check is that the norm of any element of Rn is greater than or equal to 0. Okay, that's obvious because we're taking a sum of absolute values and then a certain power of it. Secondly, we have to check that x1, the norm of x1, xn is 0 if and only if all the xi's are 0, or the xk's, since I'm using k as my generic index, as my enumerating index. Okay, so we can also see this quite plainly. Then we have to check homogeneity. Again, this is very, very simple. So if we take lambda times one of these elements, and I'm forgetting to put the subscript p. So we will have lambda x1 all the way to lambda xn. And this is going to be the sum from k equals 1 to n of lambda times xk to the pth power all raised to the 1 over p. And of course, you can see that these powers have been arranged so that once lambda exits all of them, it's simply its absolute value, right? So you will get the absolute value of lambda raised to the pth power here times xk to the pth power all raised to the 1 over p. And I think I'm giving more details than one should give here, but if you see this for the first time, I'm guessing that these details do not hurt anyone. So all of it to the 1 over p. And finally, when we apply 1 over p to all of them, we get the absolute value of lambda here times sum from k equals 1 to n of xk to the pth all raised to the 1 over p, which is simply absolute value of lambda times the norm of x1 up to xn. And of course, that checks homogeneity. Now, the one which is usually the hardest one is simply the Minkowski inequality. So the reason why x1 plus, or rather the norm of the sum x1 up to xn plus y1 comma yn is less than or equal to the sum of the corresponding norms. That's precisely Minkowski's inequality. So this means that Rn with this norm, so Rn with this P norm, is what we usually denote as LP, and we put a subscript n, implying that this is the finite dimensional analog with dimension P. And of course, like every finite dimensional space, it is complete. It is a Banach space. The completeness actually here is pretty straightforward to check, because if you get a Cauchy sequence of such elements, then you can show that you get Cauchy sequences coordinate-wise, and then they converge. And then if you form the element that has as its coordinates the limits of those sequences, it's immediate to show that the sequence, the original sequence, tends to that element. So the point here is to define LP as the infinite dimensional space. So here we talk about sequences. So LP now will be, by definition, all the sequences xn, n in n, such that the sum of the pth powers of these sequences is less than infinity. And the norm of such a sequence, the p norm if you like, I'm going to drop the subscript p because we're not going to work with any other norm in the rest of this video. So it will be simply the sum of the pth powers all raised to d1 over p. Okay, so that's the norm. Now let's discuss why this is a norm space. And to understand why this is a norm space, actually, again, the only sticky point, I think, the first three properties can be literally repeated for infinite sums instead of finite sums. There's absolutely nothing that changes. For the triangle inequality, we have to be a little careful. Also, one has to ask here if given two elements in LP, whether their sum is in LP. Okay, obviously one has to ask that because we have a convergence condition. And of course, the idea here is pretty simple. Let me show you how this is done. So what you do is you first apply this for truncated sequences. So let's say you start with two elements. So let's say that x and y belong to LP. So x is a sequence xn whose sum of pth power converges, and y is a sequence yn whose sum of the pth power converges. So what you can do right away is apply the Minkowski inequality for truncations of these sequences, meaning we don't go all the way to infinity, we stop at n. So we will get that xn plus yn to the pth power. The sum of these will be less than or equal to the sum from n equals 1 to m of xn to the pth power all raised to the 1 over p plus the sum And now the idea is pretty simple. Somebody might say, okay, take the limits as m tends to infinity. And that's actually not quite wrong, but there's a more elegant way of saying that. Now you can say that the sum, the finite sums on the right-hand side are less than or equal to the infinite sums that are known to be finite numbers, right? So the infinite sums converge, series converge. Okay, and now you have an expression that depends upon m, which is always less than or equal to this number, which is a constant number. This is a non-negative real number. Okay, it doesn't depend on m. So now you can say there the supremum as m of all these sums as m tends to infinity, or the limit as m tends to infinity. So you can consider it as a finite sum. As the partial sums of a series. And so as m tends to infinity, what you get is that the sum from n equals 1 to infinity of xn plus yn to the p power, all raised to the 1 over p, is less than or equal to sum from n equals 1 to infinity of xn to the pth power plus the sum from n equals 1 to infinity of yn to the pth power all raised to the 1 over p. And pretty much that gives you that x plus y is finite, and moreover, I'm sorry, the norm of x plus y is finite, and moreover, it's less than or equal to the norm of x plus the norm of y. So this means that we have a norm linear space, and more importantly, we would like to show that it's complete. So the last claim is that LP is complete. And now what we have in our hands is pretty much a repetition of the argument that we did for L1, but let's recall the most important parts. So the most important parts are to take a sequence. So here we will have to jungle a little with the indices. So let xm be a Cauchy sequence in LP. So xm, each xm is a sequence, right? So each xm is something like x m comma n for n in Z. And we know that the sum from n equals 1 to infinity of x sub m n to the pth power converges. Okay, so that's what we know. And also we have that xm minus xl norm tends to 0. So what this really means is that sum from n equals 1 to infinity of xm n minus xln to the pth power tends to 0 as m comma l tend to infinity. Again, it would be nice to write this in terms of epsilons and also bounds for lower bounds for L and M, but we're going to do this in a second. We're just saying what this means. And pretty much now what we need to do is notice that xm comma n minus xl comma n to the pth power is less than or equal to this sum. That tends to 0. So for each given n, x mn for m in z now, I'm sorry, not in z, in n, this is Cauchy. So let xn be the limit as m tends to infinity of xmn. Okay, so now the argument is, what we need to do is show that we have to show two things. We have to show that x equal to xn for n in n belongs to LP. And secondly, we have to show that xm tends to x in LP. Okay, so we have to show both things. And pretty much both things are done simultaneously. So we fix an epsilon greater than 0. Then we have that there exists an n uppercase, let's call it n uppercase, such that for, in previous videos, I think we have called it m naught. So yeah, that's where we start jungling with the indices. So I'm still trying to decide what we should call it here so that we have the least amount of complicated looking things. So it's fine. Let's call it n. So we will have that xm minus xl is less than epsilon over 2 for m comma l greater than uppercase n. Okay. So now the idea here is pretty simple. We start by taking the finite sum. So you go from n equals 1 to k of x mn minus x ln to the pth power, all raised to the 1 over p, that's less than epsilon over 2, right? We know that this is true if k is replaced by infinity. So if we go all the way to k, where k is some fixed number for fixed k, this is less than epsilon over 2. So now the trick is to pass to the limit as L tends to infinity. So if we pass to the limit, if we let L tend to infinity for fixed m, which is greater than n, then what we will have is that the sum from n equals 1 to infinity to k of x m n minus xn, xn is the limit of xl comma n as L tends to infinity, to the pth power all raised to the 1 over p is less than or equal to epsilon over 2. We pass to a limit, so we have to pay the price of replacing our strict inequality with a weak inequality. Excuse me. And now this is true for any k. I mean, we fixed the k so that we were able to do that, but it's true for any k. So that will give us that the sum from n equals 1 to infinity of x mn minus xn to the pth power all raised to the 1 over p is less than or equal to epsilon over 2 when for m which is greater than n. Okay, so now we have done this for any epsilon greater than 0 by choosing any epsilon we like. I mean, you could do it for epsilon equals to 1/2. You would have that xn is, or the element x if you like, is simply the element xm minus the difference xm minus x. Yes, but this difference of xm minus x belongs to LP. That's precisely what this inequality says. And this also belongs to LP. And we have discussed that this is a vector space, so that shows you that X belongs to LP. So the candidate limit is actually an element of LP. And finally, if we read this inequality carefully, this is, by the way, less than epsilon. That tells us that xm minus x is less than epsilon for m greater than n. And that simply means that xm, the limit as m tends to infinity of xm is x, which means that we have shown both things. I don't think we skipped any details, and that's a full proof that LP is a Banach space. And that's all. Thanks for watching.